Questions about anything? Well, I'm going to do this. This is a complex version of the Fourier transform today. I'm going to demonstrate what it's good for. And I would call it the standard version because it's the one that's come to be the most natural and easy to write down and understand. But all the versions I've given you so far, the real Fourier integral, they're all basically the same thing, just different ways of writing it down. The complex version has some virtues, though, being particularly symmetric and simple when it comes to writing things out. Anyway, I'm going to motivate the thing like I did before, taking a function with compact support, meaning the support is that's the closure of the set where it's not zero. And that's a compact set, which means it's closed and bounded. So that means that the function I'm looking at is, I'm going to take it be C smooth, 2 smooth, and it's going to be 0 outside some big symmetric interval. And the idea of getting the Fourier transform is to get the Fourier series on a bigger and bigger interval from minus L to plus L. And we derive the formula for Fourier series using different intervals than the minus pi to pi. And we got a sum as n goes from minus infinity to infinity of Fourier coefficients Cn, and instead of e to the I pi e to the I nx here, we had e to the I n pi x over L. Those are the basic Fourier orthogonal functions, and where the c's were given by, instead of 1 over 2 pi, it would be 1 over 2L, integral from minus L to L, of f of t e to the minus I n pi t over L, dl. Okay? And if you write that out, if I put the formula for the CNs inside that sum, I'd get the sum as n goes from minus infinity to infinity. Let's see. Yes. Let's see. So the CNs are going to be 1 over 2L integral from minus L to L of f of t e to the minus I n pi t over L. Let's see, I'm going to write it like this. N pi over L times t dt and then I'll have here e to the I n pi over L x. And let's see, so I want to make this look like an integral. And the n pi over L's are going to be function, or this is the w axis, and the w's, let's see, I'm going to have negative, I'm going to have a 0 here too, so I'll have 0 pi over L minus pi over L, 2 pi over L minus 2 pi over L. Those are like the delta W's. So I'm going to call n pi's over L's, I'm going to call those the WN's. They occur in two places, here and here. And then am I thinking of that as WNs in a Riemann sum? Then I need a delta W. And the delta W would be a pi over L. So I give myself a pi right here. And if I give myself that pi, I'd have to divide by pi out in front. And because f has compact support, I can replace this by minus infinity without changing the integral. And I can change this one to plus infinity because f has compact support. Okay. And now when you stare at that for a minute and realize, oh, if I let the, now I can let the, now I can look at that and see, oh, that's an integral. And if I think of the WNs as the points in the Riemann sum and the delta, so this is pi over L is the delta W. Anyway, if you stare at it a little while, you come to the conclusion that as you let the L go to infinity, that is going to tend to, see, there's a 2 that comes out, 1 over 2 pi times the integral from minus infinity to infinity of an integral from minus infinity to infinity of f of t e to the minus iwt dt times e to the iwx dw. So f of x is given by that integral. And this is the Fourier transform of f. And this is this other integral is how we undo the Fourier transform. Okay, but there's going to be an annoying thing here is that there's a 1 over 2 pi. And the question is, should I put the 1 over 2 pi in the Fourier transform, or should I put the 1 over 2 pi in the thing that undoes the Fourier transform? And I guess Stein chose to put 1 over square root of 2 pi in both of them. Okay. So where to put the stupid 2 pi? Okay, and that's the Fourier transform, and this formula here is the Fourier inversion formula. So here's some conventions. And they're different in different books, unfortunately. Different books put the 2 pi in different places. I believe Stein does this, so we'll call this the Fourier transform, f hat see, what did I have? I had f hat. I kind of like an S for that, just out of tradition. That's 1 over the square root of 2 pi integral from minus infinity to infinity of f of x e to the plus I s x dx. I'm sorry. This one's minus. Okay. Okay, that's the complex version of the Fourier transform, and we also write sometimes f hat of s is the Fourier transform with no s or c, so this just the plain old Fourier transform of f. Sometimes that's a convenient notation. And the Fourier inversion formula is that you get f of x back if you put another 1 over square root of 2 pi, so they both have that in them, integral from minus infinity, and it kind of looks like you're doing the Fourier transform again, except this time you do a plus I sx ds. Okay. So you undo the Fourier transform by kind of doing the same thing except with a plus I instead of a minus I. And that kind of symmetry makes this the preferred notation. Okay, and so we also write f, I'll write g. G upside down caret of x is the 1 over the square root of 2 pi integral from minus infinity to infinity of g of s e to the plus I s x ds. So that's the upside down caret is the inverse of the Fourier transform. Another way we will write that is f inverse. That's the inverse Fourier transform. And it kind of doesn't matter what you call the variable. The x could be any old variable you want. I could replace x by t, whatever you want. Okay, so let's see. So the inversion formula when you would use this notation, f is equal to f hat upside down hat or f inverse of f stuff like that. Okay. So the big properties that are going to make this a useful thing. First of all, we have the inversion formula. I guess, yeah. Here's the reason this notation is good here, because to put a f prime hat is kind of a weird thing to look at. But the Fourier transform of f prime turns out to be I times s times the Fourier transform of f. And if you do it twice, then of course the second is comes out, and is squared is minus s squared. So the Fourier transform is going to turn differential equations into algebra equations. And then, of course, you want to know if this really works, and there's a theorem that if f is piecewise C1 smooth and absolutely integrable of the absolute value of x dx is finite. That's what it means to be absolutely integrable. Then the Fourier inversion holds I'll have to put quotes here like I did before. Quote, it's equal to the inversion formula. Let's see. That's the inverse of the Fourier transform. In the sense that where f is continuous, this would be f of x. When f is continuous at x, of course it's C1 smooth, so it's got to be, where it's differentiable and nice, it's continuous. But being C1 piecewise C1 smooth means it could have jumps. And so at a jump, it's equal to the midpoint of the jump. At jumps. So just like the Fourier integral. And demonstrate what this is good for, I like to solve this hot wire problem, but this time it's going to be an infinite wire. Okay, so I'll have an infinite hot wire. That's the x direction. And let's see, for the purpose of illustration, I'll take the initial temperature to be 0 to the left of -1, and then +1 between -1 and +1, and then 0 to the right. So this is the temperature. That's going to be the initial temperature of my hot wire. So let's see, that's equal to 0 to the x less than -1, 1 between -1 and 1, and 0 for x bigger than 1. That's going to be my initial temperature. And the hot wire problem would be the heat equation, du dt equals c squared times du dx squared. And I think I'll take c to be 1 just so I don't have to write c all the time. And now this time there's no boundary conditions, but there is an initial condition. The temperature at time 0 is going to be this f of x. No, that would be the wave equation. This is the heat equation. Okay, that's the problem. And notice that there's no boundary condition, because there's no boundary. There's no boundary, so no boundary conditions, which makes this a different kind of problem. There is a secret condition here I have, namely there's finite energy in the system. I start out with this little hot spot from -1 to 1. That's a finite amount of heat energy, and that's kind of important for a problem like this. If the temperature was getting gigantic for big X or something, that would be bad, something bad. Okay, the big idea is to hit the PDE with the Fourier transform in the space variable. Apply f in the space variable x. Okay. So let's write u hat of st is going to be the Fourier transform in the space variable of u, and that would be 1 over the square root of 2 pi, integral from minus infinity to infinity. Integrating with respect to x, the t floats along like a parameter, and here I'd have e to the minus sx dx. Okay. And now you think about what is this going to do to, how am I going to use the PDE? And so you look at that PDE for a second, and think about if I took d by dt of this thing, of this, I would get du hat st dt, and presumably I could take the derivative underneath the integral sign. And that would give me a du dt in here. And this is this is going to satisfy the heat equation. So this is equal to d2u dx squared, a second derivative. And so what I'm taking here is the Fourier transform of a second derivative. And we know the Fourier transform, that's going to spit out minus s squared times the Fourier transform of u. And t is floating along like a parameter. So what I get, hopefully it will be justified, is that du hat dt in s and t is equal to minus s squared u hat of s of t. Put that in a red box. And that feels like an ODE. An ODE with a parameter. I'll put ODE in quotes because, of course, there's two variables. With a floating along parameter. T. Oh, the other parameter is S, with a parameter S floating along. And we solved something like it last time. This time, u hat would be complex valued, but that's no big deal. The solution to this ODE is that u hat would be exponential growth. So there'd be a constant here times e to the minus s squared t. And that constant might depend on s, because the parameter is floating along. Well, there's two things to notice here. This constant might depend on s. In fact, it will. On the parameter s. And it's okay to allow that constant to be complex. Because the Fourier transform is a complex valued function. For C of x to be complex. A complex number. Okay? Well, now the problem is we've reduced the problem to figuring out what that C of S is. And the key to that one is the initial condition. So the next step get C of S from the initial condition. Okay, so let's think about the initial condition. We have U hat of S comma t equals 0. That's the Fourier transform of U of x 0 e to the minus I sx dx. And at time equals 0, this is f of x. But let's see, U of S, if I look at that formula there with the red C of S, U of S at time 0 is C of S. Right? Because e to the something 0 is 1. So in fact, this is C of S. And we see that is that C of S is equal to the Fourier transform of f. And f was just it's plus 1 between minus 1 and 1 and 0 everywhere else. So that's just 1 over the square root of 2 pi. Let's see, when I integrate 0, that part goes away, so this would be the integral from minus 1 to 1 of 1 times e to the minus I sx dx. That's a pretty easy integral. Let's see. In fact, the antiderivative of e to the I sx would be, what would it be? 1 over minus is e to the minus isx evaluated between x equal minus 1 and plus 1. So that's equal to, what is it equal to? 1 over the square root of 2 pi. I guess I have to do it like this. Sticking in 1, I would get e to the minus is over minus is minus e to the plus is over minus is. Let's see, I kind of like that I on the bottom. I wish I had a 2 on the bottom. Oh, let's see. I have a minus minus. So that's e to the is minus e to the minus is. I can pull the 1 over s out. And then I have an I. Yeah, okay, that's looking good. And I look at that and think, oh, that's the sine function. So in fact, if I put a 2 here and here, that is the sine function. And so this thing looks like it was going to be a weird, annoying, complex thing. It turns out to be, what is it? Square root of 2 over pi sine s over s. Something completely clean and nice. And that means I've got my Fourier transform figured out. My u hat of s of t is square root of 2 over pi sine s over s e to the minus s squared t. And I'm pretty much done. The last thing I want to do is undo the Fourier transform. Undo the Fourier transform in the space variable, and you get that u of xt, the actual solution, would be the inverse transform of that thing. And the inverse transform of that thing would be 1 over the square root of 2 pi. Let's see. I'd be integrating as s goes from minus infinity to infinity of square root of 2 over pi sine s over s which, by the way, is a perfectly nice function. It doesn't blow up at 0 because that famous limit is 1. In fact, it's infinitely differentiable there, too. So let's see. E to the minus s squared t. And then I have to take e to the I sx ds. That's a pretty interesting formula to look at for a little while. Let's see, the square root of 2's cancel, and I get a 1 over pi times the integral from minus infinity to infinity. Let's start writing it out here. Sine s over s e to the minus s squared t, and e to the I sx is cosine sx plus I sine sx ds. Staring at that for a second, this, let's see, sine is even and s is even. So, odd. Sine is odd and s is odd. So their quotient, this is an even function. Even function of s. This is an even function of s. Cosine is even. Sine is odd. Okay. Even, let's see, even times odd would be odd. So that imaginary part integrates to 0. So I've got a symmetric interval. In the sense that the integral from minus infinity to infinity is the limit as a goes to infinity of the integral from minus a to plus a. And so the integral, even times odd, would be odd. And that would integrate to 0. Even times odd is odd. So the imaginary part of that integral integrates to 0. of the integral from minus infinity to infinity is big fat 0. And so what I get when you look at it is that my solution is this explicit thing, 1 over pi, integral from minus infinity to infinity, sine s over s, e to the minus s squared t, cosine sx ds. And that's a very well behaved integral. The functions are all in there are bounded, nicely bounded. And in fact, the sine s over s goes to 0, and e to the minus s squared t goes to 0 incredibly fast. And the cosine is bounded. So that's a very well-behaved integral. In fact, the wiggling cosine, there's a lot of cancellation, and that makes it go to 0 even faster. The Fourier transform has that similar property. It's the Riemann-Lebesgue lemma, in fact, that when you start integrating something that wiggles like hell, the wiggles cancel each other, and the integral goes to 0. We're going to see that. You'll see that in the homework that's due this week. Okay, put that in a red box. That's the solution. And it's I'm going to show you. I got Maple fired up here. Let me show you that this actually converges, or maybe make you believe that it might. There's Maple. Let's see, I use W's instead of S's here. I'm defining a function. So U, colon equals means I'm defining the thing, and I'm defining a function. X comma b is going to go to that integral from, let's see, I could have made that. Yeah, that's a symmetric. Those are even functions, so it's 2 times the integral from 0 to b. Okay, and I don't have I took t equals 0 there, so there's no s squared t. The question is, at time equals 0, what is that going to converge to? And that's what it is. Let's see, I guess I should go back. What am I doing here? Since that's a symmetric interval, that's 2 over pi, integral from 0 to infinity. It doesn't matter what I call the variable, so I'll put a w over w. E to the minus w squared t cosine wx dw. And I took t equals 0 there, so there's no e to the minus w squared t. So now when I go back and look at that integral, that's what I've got. Sine of w over w cosine wx dw. Let's plot it and see what it does. Look at that. That is like a Gibbs phenomenon. I only took b to be, what did I take it? 20. So I didn't make it go too far out to infinity, but you can see that it really is doing that, approximating that kind of step function. And there's a Gibbs phenomenon where it overshoots the jump. And it looks like it's going to the midpoint of the jump at the actual jumps. Okay, why don't I take 50 and see what happens? Change that 20 to a 50 and push return again. Gets better, but there's still the stupid Gibbs phenomenon, which is annoying. Gets closer. So that's kind of numerical evidence that these things really do what we expect them to do. if I took a nice smooth function, we wouldn't have any of those issues. The convergence would be faster, and there wouldn't be any of the Gibbs phenomenon. It'd be fun to play around with that. By the way, Maple is good at doing integrals of sine w over w from 0 to infinity. And it knows the famous formula you showed using the Dirichlet kernel. And you can have w equals 0 dot dot infinity is the what you write when you're talking about the plus infinity. Let's see let's say I want to graph the function this converges to. That's the Heaviside function. That function f of x can be expressed in terms of the Heaviside function. That Heaviside function is 0 to the left of 0 and 1 to the right of 0. The unit step function. I can plot my that function against the Heaviside function on the same graph. I guess that didn't make it very interesting to look at. Let me make it, instead of 50, let me make it 10. There. Now you can see that it really is kind of approaching that. 50 makes it get a lot closer. What the heck, let's try 70. If you get carried away, it'll work too hard. But that's even better. So there's 70. Let's see. Since I'm showing you in these last few minutes, oh yeah, let's see. Let's say you want to calculate these integrals and look at their numerical value. Obviously, Maple is doing that to make these graphs. But here's a command. Eval f means evaluate it as a floating point number. And if I put an I with a small I int here, it would actually try to find an antiderivative and calculate that integral. And of course, it can't do that. So what would I try? What happens if I put a lowercase I here? Oh, evaluate it. It'll do that automatically. Let me get rid of this eval f. I don't think it can calculate this integral. Doggone it. Sorry. Let me get rid of that. Can it calculate that? It can't calculate that. It can't find an antiderivative for that. So in the other thing, it knew that thing was pi over 2, and it wrote pi over 2. But if you give it an integral it can't do it. But you can ask it to evaluate it as a floating point number. So I used to think you had to put a capital I there, but apparently you don't. It can also do complex calculations. So in Maple, capital I is the imaginary number I. So you'll notice that calculation I did of integrating e to the I sx as x goes from -1 to +1. Maple does that just fine and gets that. And then when I played around, I simplified that. You can tell it to simplify the output of the previous command. And when I ask Maple to simplify that, it gets what I got, sine of s over s. And here, this is to convince you that I really is the thing whose square is -1. So Maple can do a lot for you. And in my office, what did I do? Let me go back to the very top. In my office, I was sitting around, and I realized, I want to show you this solves the heat problem. And so there I would need the exponential function of, what is it, t, it was minus t times s squared. In this case, w squared times that. That's let's see, now that doesn't make any sense anymore. I've got a t variable and a b variable. So I'll call it x comma t comma b. Now it's a function of both t, x, and b. And I wanted to animate that and show you that it converges to something that's the solution of the heat problem. And Maple had to think a long time to do that. It's kind of annoying. I didn't think I could do it in class. So now I've got u of tb. Let's see what happens. If I'm going to use plot, I need with plots. So I have the animate command, and then I'm going to animate u of x comma t comma b. I didn't tell you what b is. Let's make b to be 5. And then I'm going to make x go from, how about minus 6 to plus 6. Nah, minus 4 to plus 4. How about that? And then t needs to go, t is the animation variable. I'm going to make t go from 0 to 10. Maybe I better be careful in the beginning. 6. That should do it. Semicolon. It's working. See, if I go up here, you see the little hourglass? That means it's working. And I don't know if it's going to get done in time to do it. But if you got time, the bigger number you put in there, the harder it has to work, and the longer it has to work. And let me tell you what you're going to get. I'll come back to this before class is over to see if it got done. Let's see. The solution looks like this, kind of. It starts out being kind of crummy. It would be 0. It's supposed to be 0 and then be 1 for a while and then be 0 again. At time equals 0, it's kind of crummy. It would be wiggling. It would do a Gibbs phenomenon. Oops, and then wiggle. And do a Gibbs phenomenon. And then wiggle. But as soon as time kicks in, it smooths it completely out. And so it would be real small here. And then the next instant, it would smooth it out even more. And the heat very rapidly gets sucked out, and the thing flattens out, and instantly gets smooth. So it's kind of crummy at very small time, but in no time at all, it smooths out, and the heat gets sucked out, and it's just fizzles out and dies away rapidly. Let's see if Maple got done. Did it? Oh, it's still thinking. I did push return. Yeah, I did, because it's still hourglass. Yeah, I knew this would happen. That's why I had my backup plan of drawing it with my bare hands. Anyway, I'll post this worksheet so you can see it. I can't do the animation on the... Oh, yeah, I can make an animation. You can save the animation from Maple quite easily, so maybe I can do that too.